Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, and their performance across various tasks. LLMs typically use a dense architecture, meaning all parameters are applied to every input during both training and inference. This leads to higher computational costs as we increase model size. Research shows that better model performance correlates with larger model capacity, but simply enlarging the model poses challenges, such as increased hardware needs and training instabilities like gradient spikes. To tackle these issues, we have seen the rise of mixture of experts, MOEs. In MOEs, only a portion of the model parameters, known as experts, is activated for each input, which allows us to increase the total number of parameters without a corresponding rise in computation. MOEs have been shown to outperform dense models with similar computational costs. However, training MOEs from scratch can be costly and unstable. To improve efficiency, recent studies have suggested initializing MOEs with pre-trained dense models, followed by a few training steps. This method has several benefits. We can use existing knowledge from pre-trained models. The smaller dense model is quicker to train, and many pre-trained models are available in the open source community, allowing for further improvements without extra pre-training costs. Specifically, we introduce Branch Train Mix, BTX, which initializes an MOE with a set number of feed-forward network, FFN, experts through a three-step process. We create multiple copies of a pre-trained model, further train each on specific data, and then initialize the MOE's FFN parameters from these specialized models. However, we do not convert the attention layers to MOE layers. Instead, we average the attention parameters from the dense models to initialize the MOE's attention module, while the router parameters are set randomly. This method, however, does not fully utilize the specialized models for two main reasons. We miss out on the expert knowledge in the attention modules, and averaging parameters from different models can dilute their unique specializations. To address these shortcomings, we propose Branch Attend Mix, BAM, which enhances BTX by incorporating both FFN and attention parameters into expert layers. Our contributions include using a variant of mixture of attention, MOA, with soft routing, where each token interacts with all attention experts, which we validate through ablation studies as crucial for improving performance. We present two BAM variants, one that includes all attention parameters for optimal performance and another that shares key and value parameters across experts for better efficiency. To manage the increased computations from soft routing, BAM employs a parallel attention transformer architecture, allowing simultaneous computation of attention and FFN experts, thus enhancing throughput. We validate our approach with experiments on seed models ranging from 590 million to 2 billion parameters, showing that BAM surpasses the BTX model in perplexity and performance on downstream tasks across various domains under similar data and computational conditions. In the related work section, we note that recent studies have explored efficient initialization for MOEs using pre-trained dense models. Sparse upcycling simply copies parameters from a single dense model to MOE parameters, while BTX improves this by using multiple specialized models. However, both methods only focus on upcycling the FFN components of the dense models, unlike our approach. Section Summary. In this section, we discuss the challenges of scaling large language models, LLMs, due to increased computational costs and training instabilities, and introduce mixture of experts, MOEs, as a solution that allows for efficient model expansion. We propose Branch Attend Mix, BAM, to enhance the initialization of MOEs by incorporating both feed-forward and attention parameters from specialized dense models, demonstrating improved performance and training stability compared to previous methods. Section: Alternative Architecture for MOEs. In this section, we explore alternative architectures for mixture of experts, MOEs. Unlike the standard MOE models that only use feed-forward blocks, recent studies have examined a mixture of attention framework that incorporates attention experts alongside feed-forward experts. This method hasn't become widely adopted because it offers only slight performance gains and requires extra optimization techniques. However, When we repurpose specialized dense experts into an MO, using attention experts is more fitting since their parameters hold specific domain knowledge that would otherwise be lost. We also look at alternative methods for merging models. Recent efforts have focused on combining various publicly available dense models to create a better model through layer-wise merging of pre-trained weights. This results in a new dense model rather than a sparse one. Other research has investigated the dynamic addition of new blocks to a model whenever it is trained on a new domain, but this approach starts new experts from scratch instead of leveraging existing models. Next, we discuss parallel attention transformers. The typical architecture for large language models, LLMs, involves stacking multiple transformer blocks. Each block includes a multi-headed attention (MHA) module, followed by a residual connection and a feed-forward neural network (FFN). Recent innovations have led to the development of parallel attention transformers, which compute the outputs of the attention and FFN layers simultaneously using the same input. The final output combines the results from both layers, enhancing computational efficiency without sacrificing performance. We then delve into multi-headed attention. In an attention layer with multiple heads, the input is transformed into query, key, and value vectors using learned parameters. Each head processes its vectors independently to generate attention outputs. We concatenate the outputs from all heads and project them back to match the original model's dimensions, ensuring consistency across the network. Moving on to the mixture of experts, we replace the FFN layer in a conventional dense transformer with an MO layer. This layer includes a linear router and several FFN experts. The router generates normalized logits that determine which experts to activate based on their gate values. The final output of the MO layer is a weighted sum of the outputs from the selected experts. Lastly, we examine the mixture of attention, which extends MOs by substituting the traditional attention layer with attention experts. Each MOA layer features a linear router and multiple attention experts. The router produces normalized logits that indicate the gate values for each expert. Each attention expert consists of query and output projection components, while the key and value projections are shared for efficiency. The final output of the MOA layer is a weighted sum of the computations from the top selected experts. Section Summary. In this section, we explore alternative architectures for mixture of experts, MOs, including the mixture of attention framework that incorporates attention experts alongside feed-forward experts, which is more suitable for leveraging specialized domain knowledge. We also discuss the parallel attention transformer architecture that enhances computational efficiency by processing attention and feed-forward layers in parallel, and we detail the mechanisms of both the mixture of experts and mixture of attention layers, highlighting their routing and output processes. Section BAM, Branch Attend Mix. In this section, we describe the BAM, or Branch Attend Mix, approach, which consists of three main phases. First, in the branching phase, we create multiple copies of a pre-trained dense model, which we will call the seed model. This seed model uses a parallel attention transformer architecture. We choose this architecture for two reasons. It provides better processing speed compared to traditional transformers, and it allows our mixture model to benefit from this efficient setup, enabling simultaneous calculations for attention and feed-forward networks, which improves both training and inference. Next, during the continued pre-training phase, each copy of the seed model is independently trained on a specific mix of data tailored to different fields like law, mathematics, and coding. This results in specialized models that perform better in their respective areas, although they may struggle outside their specialties. In the mixture model training phase, we start with the specialized models from the previous step and also include a copy of the original seed model. This ensures that the general knowledge from the seed model is retained in the mixture model. A key feature of BAM is that it fully utilizes the specialized models by using both the attention and feed-forward layers. The parameters for each expert in the mixture model are taken directly from their corresponding specialized or seed models, while other parameters are averaged from the dense models. The router layers are initialized randomly. This approach maximizes the use of specialized capabilities and avoids the performance issues that can arise from averaging attention parameters. We will further elaborate on the training methods for the mixture model. For the attention experts, we adapt the MOA architecture, which traditionally uses only certain projections as experts, by implementing soft routing instead of the usual top K routing. This means that each input token is assigned to all attention experts, which we find crucial for better performance. Additionally, we include key value projections for each attention expert rather than sharing them, allowing us to fully leverage the specialized attention capabilities. In the FFN experts training phase, we typically use top 1 routing. To maintain stability during training, we apply auxiliary losses to encourage balanced load across experts and to manage the router's input values. The final loss function combines the negative log likelihood loss with these auxiliary losses, weighted by specific hyperparameters. Section Summary. In this section, we describe the BAM, Branch Attend Mix, framework, which consists of 3 phases: branching from a pre-trained seed model to create specialized models for different domains, continued pre-training of these models, and mixture model training that leverages both attention and feed-forward experts for enhanced efficiency. We also introduce modifications to the attention routing mechanism and implement expert parallelism to improve training stability and performance. Section: Experimental Setup. In this section, we validate our model, BAM, against the baseline model, BTX, through 2 different scales of experiments. We provide detailed architecture specifications in the appendix. For both experiments, we train a mixture model that combines 4 dense experts, a general pre-training seed model, and specialized experts in code, mathematics, and law. Each expert is further trained using 100 billion tokens. We utilize the Atom W optimizer with a weight decay of 0.1. To maintain training stability, we set the peak learning rate for the continued pre-training phase to half of that used in the initial pre-training phase. For our small-scale experiments, we use a dense seed model with 590 million parameters, pre-trained on 400 billion tokens, with a batch size of 1 million tokens. We implement a learning rate schedule that gradually increases from 0 to a peak of 0.00012 over 1500 steps, followed by a cosine decay to 10% of the peak rate. In the large-scale experiments, we work with a dense seed model containing 2 billion parameters, pre-trained on 750 billion tokens, and a batch size of 4 million tokens. The learning rate schedule here warms up from 0 to a peak of 0.01 over 2000 steps, then decays to 3% of the peak rate. During the mixture model training, we notice gradient spikes when using the same learning rate schedule as before. To address this, we reduce the peak learning rate to 0.0001 and the warm-up steps to 1000, followed by a cosine decay to 10% of the peak rate. Next, we detail the data used for both BAM and BTX experiments. Each dense expert is trained on specialized data domains for 100 billion tokens. The mathematics domain includes datasets like MathGLM, GSM8K, ProofPile2, and MathPile, ensuring no overlap between the training and evaluation splits of GSM8K. The code domain consists of the StarCoder dataset, while the law domain includes the pile of law and HUPD datasets. We also augment each domain with 10% data from Common Crawl. Our ablation experiments show that adding some general text data improves model performance by better aligning the expert data distribution with that of the seed model. During the mixture model training, we ensure an equal distribution of data from each domain, with each contributing 25% to the overall mix. For evaluation, we compare BAM to BTX, the original dense seed model, and the dense expert models. We assess BAM in 2 settings: data matching, DM, where we use the same training data as BTX, and compute matching, CM, where we match the computational resources used for training. In the small-scale experiments, we allocate 25 TPU core days for all Mo training phases, while in the large-scale experiments, this increases to 305 TPU core days. We evaluate perplexity and also assess performance on zero-shot and few-shot downstream tasks relevant to each expert domain. For mathematics, we report average performance on GSM 8K and math. For code generation, we evaluate on Human Eval and MBPP. For law, we use the International Citizenship Questions subtask in Legal Bench. For general knowledge, we report on natural questions and trivia QA. And for reasoning abilities, we use various tasks like ArcEasy and Wino Grande. We also test general language understanding using MMLU. Finally, we evaluate two variants of BAM. BAM, Expert KV, which uses all attention parameters in the attention experts, and BAM, Shared KV, which shares key value projections among all experts. We report on both variants since each has its advantages. BAM, Expert KV, shows better performance due to increased specialization, while BAM, Shared KV, is more efficient in terms of memory usage and inference speed. A more detailed analysis of inference efficiency is available in a later section. Section Summary. In this section, we validate BAM against the baseline model BTX through small and large-scale experiments, utilizing a mixture model of specialized experts trained on 100 billion tokens each. We detail our training setups, data domains, evaluation metrics, and compare two BAM variants, highlighting the trade-offs between performance and inference efficiency. Section: Perplexity Evaluations. In this section, we present the results of our perplexity evaluations for both dense models, which include seed and specialized dense models, and generalist models like BAM and BTX. Our small-scale experiment results are shown in one table, while the large-scale results are in another. Throughout our experiments, we consistently find that BAM outperforms BTX in both compute and token matching scenarios. Although dense expert models can excel in their specific areas, they generally fall short compared to generalist models in other domains. Next, we provide benchmark evaluations for downstream tasks in large-scale experiments, where all BAM variants outperform BTX on average. We do not include small-scale downstream results since they mostly resemble random guessing, likely due to the limited model scale. We also explore the significance of upcycling attention experts in BAM by comparing it to BTX, ensuring both models have the same total and active parameters. All our ablation experiments use 100 billion tokens during the mixture model training phase. For matching total parameters with BTX, we increase the number of feed-forward network (FFN) experts while maintaining top-1 routing. We find that BTX matches BAM's total parameter count by using 6 FFN experts. Even when BTX increases its FFN experts to 8, BAM still outperforms it. To match both total and active parameters with BAM, we adjust the routing from top 1 to top 3 in every mixture of experts (MO) layer of BTX. We observe that BTX matches BAM in both total and active parameters with 6 experts, 3 of which are upcycled from 3 dense models and the other 3 from the same seed model. However, despite this parameter matching, BTX does not surpass BAM. We then compare soft routing with common sparse routing methods, such as top 1 and TOP2, in BAM's attention expert layers. Our findings indicate that BAM with top 1 and TOP2 routing does not improve over the baseline BTX in most domains, while BAM with soft routing consistently outperforms BTX across all domains. This highlights the importance of using soft routing in our mixture of attention layers. In our analysis of inference efficiency, we examine the floating point operations per token for BTX versus BAM. We provide estimates for non-embedding parameters per transformer layer, excluding negligible components. While BAM consumes more flops due to soft routing attention experts, this increase is somewhat offset by our parallel attention transformer architecture and expert parallelism. When comparing flops between BAM and the parameter matching version of BTX, we find that BAM has a similar flop count while delivering better model quality. For empirical inference latency, we measure the time taken to generate 16 tokens from a 256-length prompt, averaged over 10 runs on TPUs. We find that BAM is slightly slower than standard BTX, likely due to increased memory pressure from individual key value caches maintained by each attention expert. To address this, our KV sharing version of BAM reduces inference latency from 6.17 seconds to 5.96 seconds by allowing all attention experts to share a single KV cache. In future work, we aim to further optimize inference time to align more closely with the standard BTX baseline, as our current setup is more focused on training than on inference latency.